Hello, this is Unit 7 on the Raspberry Pi, and we're going to look at the GPIO in this unit. So we'll start first with some photos of Northampton. So this is the town hall, and this is a morning shot. There was fog in the valley, and then the sun lifted, the fog disappeared, except right over here, that's fog over the Connecticut River. And you see the town hall right here, and on the other side of this, behind where I was when I took the picture, is Smith College Hall, and the two steeples of St. Mary's, and that's a sunset. The sun is setting behind St. Mary's right here. Okay, so that's Unit 7. We're going to look at the GPIO. So in Unit 6, we did the unboxing, we explored Raspbian, talked about Raspbian, how fast is a Raspberry, talk about internet address, remote connection, SSH, and VNC, so we're all set with that. So this unit, we're going to deal with the programming to GPIO. Next week, we'll have more units, and in these units next week, we're not going to deal with the hardware. It's going to be mostly Linux administration, how to administer a system like this Raspberry Pi that runs Raspbian, a version of Linux. And we're going to install applications and look at this system as a server, headless server that we connect to through either VNC or SSH. So the GPIO stands for General Purpose Input Output, and it's this connector right here, 40 pins. And so if you look at it this way and put the pins on the side, then pin 1 is the top left. So remember that. If you look at the Raspberry Pi with the connector on the right hand side, pin 1 is this one. So here, this middle block here of circles represents these 40 pins, and the numbering is that this is pin 1, pin 2, pin 3, and you see that here, this 3 means that's pin 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, so you see all the odd numbered pins are on the left and all the even numbered pins are on the right. So when the pin doesn't have a particular input or output, particular function, I've written down instead of the number either 3.3 volts or 5 volts. So you see we can get 5 volts or 3.3. 3.3 is the operating voltage of the Raspberry Pi. 5 volts is just provided for convenience, but nothing on the Pi actually uses it. We get 5 volt here because this little connector that we have here for power is a USB connector, and we get 5 volt from USB. So 5 volt is available, but the Pi operates at 3.3. So we have several grounds. So if you need to connect to ground, we have several of them, and they're distributed throughout the connectors, which is good. You don't want them to be all in one place. And another 3.3 volt here. And some pins are multiplex. That means that they can be used as something else. So they all the pins that are not power or ground can be digital input or digital output. And some of them can also be like pulse width modulation. We've seen that with the Arduino. Some of them can be used as clock, and then serial, we're going to see there's a serial, there are serial pins for connecting to a serial port, I2C pins, and some others. So that's that. So try to remember that when you look at it, top right corner, pin 1 inside. So that's pin 1 when you look at that. Okay. The other thing that I want to start introducing, because it's going to be a source of confusion, is that when we're going to be kind of programming in Python with a library called GPIO, the pin numbering is going to be different. Interesting. So pin 3, physical pin 3. So I'll refer to these pins here as physical pins. So that's the pin number of that of the pin here, the physical pin. But so this pin will be pin 2 when we program in Python. So we'll say I want pin 2 to be an output, so this will be this pin. And so we have a different assignment here, and you see it here. So if we want to use this pin in Python, we'll say pin 23. All right. And just to make things more fun, when we program in C with the wiringPi library, the pins will be different still. So this pin, which is pin 3, will be pin 8 with that library. So if we want to access this pin in C, we'll say we're going to use pin 8. All right, it's the way it is. So that's why I put together this, this table to really help us figure out what's what. All right, so I'm going to do some work with physical pin 11, which is pin 17 in Python, you'll see that, and pin 0 in C. So when in C we're playing with pin 0 and in Python pin 17, it is the same pin, it's physical pin 11. So GPIO, it has 40 pins. All except power and ground can be programmed as digital input or digital output. This is important. We cannot do analog with the Raspberry Pi unless we add some hardware. There are some analog to digital or digital to analog converters out there. You can add them easily, but not the native Raspberry Pi. So only digital. 5 volt and 3.3 volts are available. Again, 5 is for convenience, but the Pi operates only with 3.3 volts, which means that if you want to connect to an Arduino using the I2C protocol, you have to be careful. And that's one of the videos I've recommended earlier for you to watch as part of the project for CSC 270. So when an output on a digital pin is high, it's going to be 3.3 volt. That's the max that high will be. Ground will be 0, or ground is always 0. There are some pins that will be able to program in pulse width modulation, and here we're going to have a choice. And the reason is that the Pi is definitely a much faster processor than the Arduinos, so the Pi processor can energize pins in software quite fast to do pulse width modulation. So all the pins can do pulse width modulation in output, but that's through a library. So it will be a function that will alternate on off very fast. Can do that. But we also have some hardware pulse width modulators on board. We have 4 of them, pin 12, 13, 18, and 19. So that's what these numbers are here. So if you do it in hardware, that means that the hardware is taking care of the pulse width modulation. You tell it the duty cycle, and then it's going to take over. If you do it in software, that means that there's a little function that can run in a separate thread, so it will be in parallel to your code, and it will go and activate on for a while, and then off for a while, and on for a while, and in an endless loop in a separate thread in parallel. So you'll still be able to program other things in your program, but that's the difference. The serial communication with the SPI protocol, I haven't covered that, but it's available. I2C I have covered. We covered it with the Arduino, and that's when I connected 2 Arduinos together in a previous unit. So the Pi supports that, and that's on pin 2 and 3. So there's only one I2C port, and actually we can connect a Raspberry Pi to an Arduino as long as the Raspberry Pi is the controller and the Arduino the worker. So that's a video that is available on the project page. And then serial, we can do serial as well. Pin 14 and 15 correspond to transmit data and receive data. But again, it's 3.3 volts, so we have to be careful with that. Good link here to all this. Now, there's 2 utilities, and actually they are already installed on your Raspberry Pi because we've installed 2 of the libraries that are required to program in C and Python. So I'm going to show you pinout. So all right, clear. So the first one is pinout. So if you run pinout, it's going to take a while and gather some statistic, and it's going to output. This is called text graphics, so it's just using text to display something graphically with colors. So it's showing here the GPIO, showing the USB ports, the net. So it's giving us a nice little simplified view of our Pi, but it has found out that what we're working with is a Pi Model 3B Plus version 1.3. And it's giving us some techie information about what we're using. SoC, system on a chip, that's a microprocessor, plus all the ports inside. That's that particular chip. We have 1 gigabyte of RAM, 1024 megabytes is 1 gigabyte. and it is stored on a micro SD. That's the micro SD that you put in. 4 USB port, excluding the one for power. There's an extra port for power. Ethernet port, there's one, Wi-Fi and Bluetooth. By the way, Bluetooth is available, so we can connect to that. There's one camera port and one display port. And then it's displaying the GPIO. So this is the GPIO, and that's a nice way of getting an idea of what the different pins are. It's not as complete as the table that I have I've just shown previously, but that's a nice nice way to display it. And then there's another utility called GPIO, and if you say GPIO, actually GPIO by itself is a nice command because it allows us to access pins as input. And you can program the Raspberry Pi pins from the command line using GPIO, this app. It's kind of quite nice. So you can just at the keyboard turn an LED on and then decide to turn it off without writing a program. So, let's see, that's not good. So, all right. So this is GPIO read all. That's a command that I've just typed, and it gives us a better description in some way, more complete of the different pins. So that right here, that's the GPIO header. These are the different pins, and it's going to tell me, which ones are programmed as input and which ones are programmed as output. And right now, I haven't run any of my demo programs. Otherwise, some of these would change to output. Let me go to the C program. I should be able to see that better. So I'm going to run the Blink program here. Okay, my Blink program is running. Actually, let me run it in the background. Okay, so now I can repeat my GPIO command. Now I see it. See, this pin 11 is now an output. So I can see that I have changed one of the pins to be an output pins. Everything else I haven't touched, and so therefore they still remain inputs. So anyway, 2 command lines. Let me go back to where we were. Okay, so we're going to look at how we can program the Raspberry Pi. So first, we're going to look at how to do it in C, which is the same language we use in the sketches for the Arduino, but you're going to see it's slightly different because now it's going to be a real C program. So the library that I've picked the server is wiringPi, and written by this person who unfortunately has been fairly fed up with the way he's been treated by the Raspberry Pi users out there, that he decided to not support it anymore. So it's really too bad. People should be a little more understanding. Anyway, there's a nice post that he has explaining that. So that's the library we're using. I think it's worth going to wiringPi and explore this a little bit. wiringPi library. Okay, so that's the page. Example, so there's several different examples. Blink, and the reference set up core functions. Let's take a look at core functions. That will give you an idea of what's available. Pin mode, that sounds like Arduino stuff. You can indicate which pin is going to be working as input or output. So there's input, output, pulse width modulation output, GPIO clock as possible. Pull up, down control, digital write, okay, so that we've seen before. Pulse width modulation write, digital read, and now these analog read and analog write are going to be useful only if you have extra hardware added to your Pi. But so they'll be useful in that case, but not for us. The Raspberry Pi is not as good at doing input-output as the Arduino. However, it's much faster, as we saw. Back here, so these are just the functions that we saw. Now you know where they are and how to look at the description. So I have several demos, and we're going to look at several programs, and that's the setup that I'm going to be using. So I have my Raspberry Pi. I've used Fritzing, by the way, to generate this. I have two LEDs, and that's because that was left over from the Arduino. My Arduino setup, I just switched the Pi or the Arduino for the Raspberry Pi. I have a switch here, and that allows me to do a very simple finite state machine. So that's my setup, but it's great because now I can do blink and I can do different kinds of experiments with the switch. And so the green LED, so I couldn't find a green LED with fritzing, so I have two red LEDs, but I used a green wire here, so that's my green LED, and a red wire, that's my red LED. So the green LED is physical pin 33, right here. The red LED is connected to this physical pin 11, right here. And the switch, right here, one side is connected to ground, so this is ground, and the other side, orange, is connected to pin 12. So 11 and 12 are facing each other, right here. So that's the programming model. So let's take a look first at the organization of a program in C. So that's a typical C program. The sketch, remember, for the Arduino doesn't have a main program, you just have setup and loop. So here you don't have that, this is just pure C. I'm including the wiringPi library. I'm not doing any display on the screen because my Arduino is not connected to a display, although I'm SSH. So I'm including here the wiringPi library, so I'm going to include the headers for the library that I want to use. I have a main program. It's usually for C, it's an int returning program. Right now I'm putting void, I don't have any command line arguments, so I have to return 0. I have to make sure that I'm returning 0 because it's an int returning function. wiringPi setup, always when you start, set up the wiringPi library. So you have to do that for all programs. And then pin 0 is going to be an output pin. So that's physical pin 13. And then an endless loop where I'm going to digital write 0 and then digital write, digital write pin 0 high, digital write pin 0 low. Wait 1 second, so I'm using delay here, and that's my endless loop. And so 1 second for half a period, so it's a 2-second period, so it's a half hertz frequency generated by that. Okay. How do I compile that? GCC minus O blink, blink C, so blink.c is the name of my program. Minus O blink means output the executable in a file called blink. I'm going to use the same name as my program except no .c extension. And then I have to make sure, and I know some of you will forget, include the library wiringPi. Minus L, no space, wiringPi with an uppercase P, and that should work. Let's take a quick look at how I would do that. Here, clear, ls, remove everything that has a tilde at the end, remove blink, my executable, ls. Okay, so gcc output something called blink, blink.c. And here I forgot the library, so I'm getting a lot of errors. That's very likely what you will see, as I have to say wiring pi, including the library, and that's it. It has accepted it. If I ask for the list of files, I see now that I have blink, which I can run. Always remember */run from where I am now, because otherwise Linux will look in all kinds of other folders except your current folder. And now my LED, which I can see from here, is blinking. All right. Control-C gets you out of that. All right, so that's the code, that's my setup, and my red LED is going to be blinking. Here's a video demo, so let's run it. Sorry about that. I didn't look at where my phone was pointing. Okay, so that's my Blink library. So now let's take a look at how I would read a push button or a switch. So that's the program I'm going to be creating. So wiringPi.h, the header for my library. I'm creating constants here. Const int LED is 0, so pin 0 in C is 13 physical. Button pin 1, so that's my button, which is going to be connected to 12 here. WiringPi setup inside my main function, wiringPi setup. Pin mode, LED is an output, button is an input. All right, so now I've set the direction of exchange. Pull up, down control button, pull up. So what, remember that maybe I should, actually I cannot use my iPad right now. But remember that normally you want a resistor here between this point and VCC. So here from between this pin and VCC, I would want to have like a 1K resistor. But the Raspberry Pi has pull-up resistors on board, so I just have to indicate that I want to use a pull-up here, indicated here, for the button, which is pin 1, with pull-up down control. And that allows me to simplify my hardware. So I'm removing a resistor that should have been here. Then infinite loop, so remember for semicolon, semicolon, there's no initialization, there's no test, and there's no increment version, so that loop is going to go forever, will never stop. Local variable val, I'm digital read the button, and then I'm displaying whatever that value is, which is going to be 0 or 1, into the LED. All right, and that's it. So that's my infinite loop, and then return 0. I'll never get there, but I still need to have it so that the compiler is happy. Okay, and I have a video demo of that, so let's take a look. Okay, so that's it. So now let's take a look at how to program, do the same thing, but in Python. I'm going to see it's a very, very different approach. So I'm going to go there. The library that I've picked, and again, there's several different libraries, the GPIO0 library, and that's the API, Application Programmer Interface. So we're going to go there. So now the approach that is taken in Python is to say, well, we're going to have classes for all the different kinds of devices that I can connect to my Raspberry Pi, including LEDs and buttons. So there's an LED class, okay, and I'm going to import it from GPIO0, already installed in the SD card that you've received. And therefore, if I want to create a LED object, I'm going to say LED equals uppercase LED, comma 17, pin 17. So in Python, pin 17 is the same pin as 0 in C, which is physical pin 13. All right. And then if I want to turn it on, I say LED dot on. So on, there's going to be a method of the class LED. So I have all kinds of different methods available to me. And you see here that the Python is creating a nice, so this library, a nice interface and taking me kind of far away from the hardware. In C, you can just turn things on or off. And in Python, you have a nice layer of comfortable methods to kind of isolate us from the hardware. It's a very interesting approach. So when you create the object LED from the class LED, you can pass several parameters. So pin, you definitely need to specify the pin. You can say if it's active high, that because if you write a 1, typically you want the LED to be on, but sometimes you're going to activate the signal that you get is the opposite of what you want to display. So you could have the object inverts the whatever the signal you give it, and it's going to display the opposite on the LED. So that's active high. Initial value, do you want the initial value when you create your LED to be on or off? And then pin factory we're not going to use. This is a sophisticated option when we don't have hardware and we want to simulate what we're doing. Blink. So blink is a method. You can tell your LED.blink, and it will blink automatically. You have to tell it how long to stay on and so on. But there's an on time and there's an off time, so you can define the duty cycle. The number of times, if you want the LED to blink 10 times, you can pass a number n. Background, this is very nice. If you set background to true, that means that that LED will blink in a separate thread. So it will do that, and then your program will continue going on. So you can have parallelism, and if you have several LEDs, they can all be blinking at different rate, and you can still have code executing. So they'll be in separate parallel threads. There's also, I'm going to use that at some point in another demo, pulse width modulation LED. Plenty of methods available for us. An RGB LED, that's an LED that can have several different colors. So it has typically 1 ground and 3 pins for red, green, and blue. So you have kind of all 3 different colors in one little bulb. And I'll invite you to explore buzzer if you want to generate some sound. So that's a simple buzzer, but you have a tonal buzzer where you can generate different notes. Anyway, plenty of interesting classes that match pretty much all the different sensors that you can expect finding for Raspberry Pi. All right, and again, that's a reminder. That's pin 11, pin 17, pin 0. All 3 here correspond to physical. So 0 corresponds to physical pin 11, which is 17 in Python. All right, so that's my Blink program in Python. So fairly short. I have to import LED for the GPIO library. I have to import sleep from the time library. And now LED, object LED, is instantiated from class LED for pin 17. And while true, forever loop, I'm going to loop forever. LED on, I'm going to print something on the screen just to see. Sleep for 1 second, LED off, so I'm turning off the LED. Print LED off, sleep for 1 second, and keep on going. So that's, again, the same thing that I had before, just to remind ourselves of what's going on. And I'm energizing only one LED here. So I have a demo. And right now I'm using VNC in that demo that you're seeing. All right, so now push button in Python. How would I code a push button? Well, I'm going to use another class. So from gpioZero, my library, I'm going to import the LED because I want to access it, and the button. So these are the 2 classes that are included in the library. I need pause, and pause, I'll tell you a little bit about that later. So LED, object LED is going to be instantiated from the class LED on pin 17. Object button is going to be instantiated from the class button on pin 18. Pull up equals true. So both the C and the Python library know that pins have internal pull-up, but I need to energize them. So pull-up equals true, so I'm going to have a resistor from the input of the Raspberry Pi to VCC, which is 3.3 volts right now. And then while true, forever, if button dot is pressed, so there is a member variable called isPressed. It's not a method, no parentheses. It's just a variable inside the element button. If it's isPressed is true, then I'm going to turn on the LED. Otherwise, I'm going to turn off the LED. So I'm just constantly reading the button and doing that very, very fast. So it's instantaneous. As soon as the button changes, the LED is going to respond one way or the other. And then here, actually, because I have this loop, I don't really need the pause, but in some cases, when I'm going to be energizing something like a blinking that is going to be in the background, when the program hits pause, it's going to stay there and not go any further. So that means that my program, let's assume that I had a break in there and I would come out of that while loop, I would be stuck there until I would type Control-C there. So it's a way of preventing a program from stopping, exiting, and then everything that's going on may crash or may stop. So pause is just, we're almost done, but we don't want the program to stop so that everything that we have instantiated can still continue working. And here's a video demo of this. Concept. So now that's it for this unit, and you're ready for the Unit 7 lab. So I'll have a lab for this unit on Thursday for those of you taking CSE 270, and you'll redo some of that. And so I want you to be comfortable with C and with Python, and you'll figure out which one you feel more comfortable with. So that's it.